All right, geometry 9-3 rotations. This is the last of the rigid motions that we'll talk about. And rotations, the layman's term word for rotations is turn. So again, you have slide for a translation, flip for a reflection, and turn for a rotation. And again, this is a rigid motion, and we'll talk about that in the next slide. Okay, so when you define a rotation, you need two things. You need a degree at which you're rotating about and a point that is called your center of rotation. Okay. Now, for our purposes, we will be using the origin as the center of rotation, unless you're in honors, and I'll show them that. So, a couple rules here. Number one, if the pre-image Q is the point of rotation, then Q prime will be Q. All right, so again, that is only if Q is the point of center of rotation. Sorry, center of rotation, not point. Center of rotation. Okay, so sometimes you do have a figure, and one of the vertices is the origin. So that point will stay put. Okay, all of the other points are going to rotate in this fashion. So let's look at V. Okay, so V is the pre-image. When you rotate it, it's X degrees. All right, here's the segment connecting V and Q, which is our center of rotation. The angle at which you rotate X degrees will be that angle formed by V, Q, and V prime. And the sides of the angles, that is the distance from the pre-image V to the center of rotation, will be equal to or congruent to the distance from the image to the center of rotation. So all of that is stated right here. Okay. All right. Now, again, most of our stuff will be done on the coordinate plane in increments of 90 degrees. But again, you can do generic rotations in space. Okay. All right. So again, you need an angle of rotation and a center of rotation, which is what you'll get. We have our idea of being a rigid motion. Again, if you look at these two pictures, the two triangles are congruent. So for instance, UV is congruent to U prime V prime, just turned, and angle W is congruent to angle W prime. So because they're rigid motion, your pre-image triangle UVW will be congruent to your image triangle U prime V prime W prime. Okay, so be aware of that. And then here's your notation. If it's going to be in function notation, little r stands for rotation. You should have a degree measure and then the point that you're rotating about. And again, unless otherwise stated, your rotations will be counterclockwise. I think Delta Math does a good job of identifying counterclockwise or clockwise, but if they don't mention anything, I believe they are thinking counterclockwise as well. Okay, so that's all about rotations. So now let's focus on the coordinate plane. All right, so there are a couple rules here to follow. So first rule here is the 90-degree rule. If you're rotating 90 degrees counterclockwise, again, all of this is counterclockwise, which would be that way, counterclockwise. So recall that when you do this, your point is going to change like this. When you rotate 90 degrees, the X and Y will flip. And if you think about this, I am going from quadrant 1, where the X is positive and the Y is positive, to quadrant 2, where the X is negative and the Y is positive. So when you flip, let me not put the X and Y, just put symbols. So when you flip your two coordinates, all right, you're going to have to change the y when it moves to the first coordinate. You have to change it to its opposite sign. Remember, anytime you see a negative symbol means the word opposite, not negative. It means opposite. Minus to plus, plus to minus. Okay, so negative means opposite. All right, so let's take a look at this example in Desmos Geometry just to verify. Okay. Okay, so I have the exact same setup they do. I even use the same point G at 2, 3. So we're going to define a rotation. So transform, we're going to define a transformation. A rotation, notice the degrees, right? We're going to rotate. The center is going to be the origin, and I'm going to go 90 degrees. Okay, so let's take point G and do this rotation, and boom, look what happens. Our point G prime now has the coordinates of -3, 2. So the x and y switched, and the first number became opposite of what it was, as stated right here. Okay. All right, next, let's take a look at the 180 rotation. All right, so when you do a 180-degree rotation, here's the rule. So the x and y stay put. So again, think of this as 290 degrees. So when the first 90 degrees, your x and y switch. But then the second 90 degrees, the x and y switch back. So eventually you're still in the same order of x and y. But now notice that you went from quadrant 1, where you are positive and positive, to quadrant 3, where you're negative, quadrant 3, where you're negative and negative. So both of your signs become opposite of what they were. Again, negative means opposite. Let's verify this in Desmos Geometry. Okay, so I'm going to define another rotation, origin, but now we're going to go 180 degrees. All right, so let's take point G and apply this rotation, and boom, look where it goes, down here. All right, so let's label that point G prime. And again, what are its coordinates? Its coordinates are -2, -3. So x and y stayed put, but one became negative, one became positive. Now, the one thing I didn't show with the 90-degree rotation, and I'll do it with the 270, is the angle, right? If you connect these 3 points with segments, you create the angle of rotation. And again, notice this is a straight angle. If I measure that angle, 180 degrees, which is the angle of rotation. I'll make sure to do that with the 270 just to show you a couple things. Okay. All right. So next, let's do the 270. So 270 counterclockwise is a big movement. All right. So you'll see it right here. Okay. So I'm starting in the first quadrant where I'm positive and positive. When I go 270, 270 is 390 degrees. Switch x and y, switch x and y back, switch x and y. So notice the 2 and 3 are switched. But this time, it's the second number that becomes opposite, because you're going into the fourth quadrant where x is positive and y is negative. The first number stays positive, but the second number becomes opposite. All right. Okay, so let's verify this in Desmos Graphing Calculator. Give me a second to erase the stuff. Okay, so now let's define a transformation, rotating it about the rotation about the origin. We're going to go 270 this time. All right, so if I apply this rotation to G, and there I go, right here in the fourth quadrant as promised, and the coordinates there of G prime are now going to be +3, but now -2. So the x and y switch places, and the second number becomes negative, or opposite. Now, if you notice here, when I make the angle, watch, G to the origin, G to G prime. Watch what happens when I try to make this angle measure. It defaults and does the angle measure less than 180. The true angle measure, well, I shouldn't say true, but one of the angle measures is this angle measure right here. Now, when you take, well, I guess we do it with circles, right, because 360. But if you take pre-calc, you'll talk more about angles above 180 degrees. That is a 270-degree angle. Okay, that's kind of odd. But just as this software did identify, if you take 360, which is a circle, and subtract 270, you do get 90 degrees. So a 270 counterclockwise rotation is the same thing as a 90 clockwise rotation. So be aware of that. And I'm going to show that to you on your notes here in a second. All right, be aware of that they are identical. Okay. So when we go back to our notes here, so again, this 270 counterclockwise, 270 counter, is going to be the same as 90 degrees clockwise. Okay, so just be aware of that as you do your assignments. And then lastly, but not very impressive, is the 361. And yes, of course, 360 means you go all the way around. So that means G and G prime are the same point. Okay, so not very interesting. All right, so I will make at least one video covering some problems involving rotations in Delta Math. All right, stay tuned.